Hello everyone, and welcome to KubeCon Europe. My name is Chen, and my partner, my co-presenter, is Wei-Cheng. I work at Anyscale, and Anyscale is the company behind Ray, the open source standard for distributed computing in Python. Due to visa issues, my partner won't be able to give the talk with me in person, but he will record a video to explain the Karmada related part of the presentation. Today, we will share a practical approach for running AI serving reliably at scale on Kubernetes under uneven GPU capacity and regional failure risks. Here is the plan. We will start the production challenges, including bursty traffic, strict P95 and P99 latency targets, and GPU scarcity, and explain why these push single cluster Kubernetes to its limits. We will then present a two-layer blueprint. The first layer is fleet orchestration across clusters. The second layer is inference serving inside each cluster. Wei-Cheng and I will split the session. Wei-Cheng will cover the fleet layer and show how Karmada applies policy for placement, replica thread spreading, per cluster overrides, and automated failover. I will cover the serving layer and show how reserve by Kubernetes RAID service, including request-driven, auto-scaling, safe upgrades, and advanced feature reserve provides. By the end, you will have a vendor-neutral reference architecture you can adapt. Now, let's start with the challenge. To start, I want to set a clear baseline. At scale, AI serving has production requirements that are stricter than most stateless microservices. First, we need predictable service-level objects. That means tight P95 and P99 latency targets, strong availability, and controlled error rates, even when traffic is bursty. Second, we need elastic capacity and GPU efficiency. Traffic can spike quickly, but scaling serving is not instantaneous. Models need one-on time, including loading large weights and initializing GPU memory. We need absorb spikes without building large queues, while also avoiding over-provisioning and leaving expensive GPUs idle. That makes right-sizing and utilization critical. Third, we need regional locality to meet latency budgets and comply with data residency boundaries. Especially relevant here in Europe, inference often needs to run close to users and within specific regions. Finally, we need safe operations and visibility. We need rollouts that are gated by health signals, clear rollback paths, and model-level telemetry such as tail latency, queue depth, and error rates. Many inference requests are long-lived, so upgrades should support graceful joining rather than abrupt termination. The goal is to meet all of these requirements at the same time. Next, I will explain why a single cluster with standard Kubernetes primitives becomes a bottleneck. Given these production requirements, single cluster Kubernetes and standard primitives fall short in two areas: infrastructure limits and serving orchestration. First is the single cluster boundary. One cluster is one blast radius. An outage, a control plane incident, or even planned maintenance can disrupt the entire inference service. GPU capacity also hits cliffs. When a region runs out of GPUs, requests start queuing and latency spikes quickly. A single physical location also can satisfy both tight global latency targets and regional data residency requirements at the same time. Second is the vanilla Kubernetes gap. Standard service and deployments are not designed for inference serving features such as multi-node and multi-GPU execution. Operationally, inference requests are often long-lived. Without serving-aware joining, a normal HPA scale-down or rollout can interrupt in-flight requests and token streams. So the takeaway is simple. A single cluster is a hard boundary, and vanilla primitives do not provide the serving lifecycle inference needs. This is why we use a two-layer design, a fleet layer across clusters, and a serving layer inside each cluster. To address both the single cluster boundary and the vanilla Kubernetes gap, we separate concerns with a two-layer architecture. At the top is the fleet layer. Karmada acts as the multi-cluster control plane and uses policy to decide where workloads run, how replicas are spread, how cluster-specific overrides are applied, and how failover works when a cluster or region becomes unhealthy. This answers the where. Inside each target cluster is the serving layer. We run reserve via Kubernetes rate service to provide inference serving capabilities such as request-driven scaling, health-gated upgrades, graceful draining, auto-scaling, and some advanced feature I will talk about later. This layer answers the how. Next, we will start with the fleet layer and go through the Karmada patterns: placement, spreading, overrides, and failover.
Hi everyone, my name is Wei-Cheng. I'm a software engineer at Bloomberg, working on the machine learning platform, and an open source contributor to the Karmada and Kubernetes projects. Unfortunately, I'm unable to join in person today due to a visa issue, so I've recorded this short introduction. In the next few minutes, I'll briefly share how we build the fleet layer using Karmada. After that, my co-presenter Henry will continue the session. Thank you for your understanding. Let's get started. Karmada is Kubernetes native. We can keep standard APIs, standard manifests, and the same kubectl workflows. If you can deploy a RAID service in one cluster, you do not need a new workload format for multi-cluster. This model is decoupled. The RAID service YAML stays stable, and all multi-cluster topology and fleet logic is expressed as declarative policies. Through policy, Karmada provides the fleet capabilities we need: placement and replica spreading, per cluster overrides and automatic failover. RAID services is a custom resource, so we use the Karmada resource interpreter to let Karmada understand RAID service status, resource requirements, and readiness semantics, so fleet policy can act on it consistently. Now, let's make the fleet layer concrete with the first policy pattern for replica scheduling in Karmada, defined in the propagation policy. First is placement. With cluster affinity, we select the clusters that meet latency or compliance requirements, such as clusters labeled for a specific region. We do this without changing the RAID services YAML. Second is spreading. With spread constraints, we require the service to be distributed across multiple clusters or regions. This reduces blast radius and avoids concentrating capacity in a single failure domain. Third is replica scheduling. For RAID services, we most commonly use duplicated. That means Karmada deploys the same RAID service into each selected cluster, and each cluster runs its own serving stack. This aligns with our two-layer design, because scaling and upgrades are handled inside the cluster by RAID service, while multi-cluster placement and resilience are handled by Karmada. Karmada also supports divided scheduling when a workload needs replica split across clusters, but it is less common for our RAID service setup. Next, once the service is running in multiple clusters, we need to adapt to differences between clusters. That brings us to overrides. The override policy is to handle the heterogeneity challenge. In a real fleet, clusters can differ in GPU labels and scheduling constraints, storage defaults, and the container registry they use. If we encode those environments detail inside the RAID services YAML, we quickly end up maintaining separate YAML per cluster. That increases drift and makes operation harder. Instead, we keep one RAID service definition and apply cluster-specific adjustment through an override policy, as shown in the diagram. The base RAID service stays the same, and Karmada applies targeted overrides before the resource is applied to each member cluster. Common examples including updating the image registry prefix for a local mirror, selecting the appropriate storage class for a model caching, and applying cluster-specific labels or environment settings needed for scheduling integration. This keeps the responsibilities clear. The fleet layer adapts environment wiring, and RAID service remains the source of truth for the service definition. With placement, spreading, and overrides in place, The remaining fleet topic is failure handling. Next, we'll cover dual-level failover. We use two-level failover triggers provided by Karmada to limit impact. First is cluster-level failover. Karmada monitors member cluster health. If a cluster becomes not ready or unreachable, it is marked with the corresponding cluster count. New scheduling to that cluster stops. And after a configurable grace period, affected workloads can be affected and rescheduled onto healthy clusters that still satisfy the placement policy based on the cluster failover policy. Second is workload level failover. A cluster can be healthy while a specific RAID service is not ready, degraded, or crash looping. To avoid relying only on cluster health, we integrate RAID service with Karmada using a resource interpreter. The interpreter maps RAID service status into health signals that policies can act on, so failover decisions can target the affected workload. That concludes the fleet layer. Next, I will hand back to Henry, who will cover RAID served by RAID service, including auto-scaling, safe upgrades, and advanced features. Thank you for listening.
Now, I'm going to talk about challenges of AI serving in production and how RAID serve and Kubernetes solves it. So the first problem is real-world AI serving isn't just one model, tensor in, tensor out. It's preprocessing, multiple models, post-processing, and business logic chained together, each with different resource needs. Traditionally, each step or deployment becomes its own service, its own container, its own config, its own deploy pipeline, which is very hard to manage. So in RAID serve, we have a feature called model composition. Instead of deploying each step as a separate Kubernetes service, RAID serve lets you compose your entire pipeline as a single Python application with independently scalable components. The next problem is inefficient GPU utilization. Many machine learning models don't need an entire GPU compute and memory capacity. In traditional serving setups, each model is assigned a dedicated GPU regardless of how much of the model actually used. A model that only needs 30% of the GPU still occupies 100% of it, leaving 70% idle. At scale, leeways translate directly into unnecessary infrastructure costs. And RAID serve provides a solution. It supports fractional GPU allocation. Instead of dedicating a full GPU for every model, you can specify the exact fraction each one needs. The model using only 30% of a GPU now requires just 30%. And the remaining capacity is available for other workloads. One configuration change, no specialized hardware. And in the diagram, this example, you can see that your GPU utilization can jump from 30% to near 100%. The second problem with inefficient GPU utilization is that modern applications often serve many model variants that share the same architecture but have different weights. Most receive sparse, unpredictable traffic. Provisioning a dedicated GPU for each is economically infeasible. RAID serve supports model multiplexing. A single replica can host multiple model variants in GPU memory simultaneously, loading and evicting them on demand by LRU caching. The router knows which replica has which model loaded and directs requests accordingly. So you can register hundreds of model variants, but only keep a handful warm at any time. Low-rank adaptation is a natural fit for model multiplexing because all variants share the same base model weight. Only the small adapter weights, typically less than 1% of the base model, need to be swapped in and swapped out. This dramatically reduces both the swap latency and the GPU memory footprint, allowing a single replica to catch far more adapters than full models. The next problem is scaling inflexibility. Traditional machine learning serving forces you to scale the entire pipeline. It treats CPU processing, GPU inference, and CPU post-processing as a single unit. So scaling for a CPU bottleneck weighs GPUs, and scaling for a GPU bottlenecks weighs CPUs. Making matters worse, default Kubernetes HPA scales based on CPU or memory utilization, not request loading. It can see how many requests are queued and processing, so it reacts too slowly for bursty inference traffic. Reserve solves this problem by scaling each deployment independently. So preprocessing, inference, and post-processing each have their own replica count. And auto-scaling policy. Scaling decisions are driven by request queue depth, not CPU utilization. When queued requests exceed the target, replicas scale up within seconds. When traffic drops, they scale back down after a configurable cooldown, which leaves no wasted resource. You can see the right example. When GPU is bottlenecked, we can only scale the GPU deployment. The next problem is development and production gap. In traditional machine learning serving, the code you write in development is like a simple Python script. It looks very different from what runs in production. For example, like you need Docker files, Kubernetes manifest, YAMLs, service mesh configs, load balancers, monitoring stakes, forcing team to rebuild and repackage their application for every environment transition. With Reserve, you don't need to rewrite anything. You just write a Python file, a serve.py Python file, test it with one line Python, a single command line. And when you're ready for production, you wrap it in a RAID service YAML and kube control apply. Same code, but just different command and all one line. The next problem is framework locking. So traditional model serving tools are tied to a specific machine learning framework or a specific cloud provider. For example, like TensorFlow serving for TensorFlow, Torch serving for PyTorch, SageMaker for AWS, and Vertex AI for GCP. When your team adopts a new framework or migrates to a different cloud, the entire serving infrastructure has to be rebuilt. Reserve solves this problem. It is framework agnostic and cloud agnostic. It serves any Python code, PyTorch, TensorFlow, scikit-learn, or your own custom logic through the same serving infrastructure. Because it's built on RAID, it deploys wherever RAID runs, any cloud and even on-prem. You can swap models and frameworks, but the serving layer can still stay the same. Right now, I want to spend some time to talk about RAID. RAID Serve is built on top of RAID, and RAID is a unified compute framework that turns complex distributed AI workloads into simple Python programs. You can use RAID to run AI workloads on any hardware, any infra, at any scale. RAID was originally developed at UC Berkeley, and AnyScale has been one of its major contributors. And RAID now is part of the PyTorch Foundation. Here are the problems RAID solved. So building an AI application end-to-end requires involving and learning a lot of different frameworks, from data processing, training, tuning, to reinforcement learning and serving. Each has its own framework traditionally. Also, every stage of the machine learning lifecycle uses a different distributed system. So glue code and operational overhead grow very, very fast. And there is a huge gap between development and production. Code that works on a laptop needs a lot of rewriting to run on a cluster. And RAID is the solution. RAID provides a unified compute layer for AI workloads. One API scales seamlessly from a laptop to infinite laptop with minimal code change. RAID open source provides 5 native libraries cover the full machine learning lifecycle under a single framework. RAID data for scalable data loading, transformation, and even batch inference. Wei-Cheng for distributed training with fault tolerance. RAID-Tune for distributed hyperparameter tuning. RAID-Serve for scalable model serving for online inference. RAID reinforcement library for distributed reinforcement learning. And these all libraries share the same foundation, Ray core. Ray runs on Kubernetes, AWS, GCP, Azure, Slurm, Yarn, or on-premise. So you can run Ray at anywhere. Now I want to spend 30 seconds to teach you how to use Ray. On the left, it is a regular Python program, a function and a class. On the right, the same code with one additional decorator, Ray.remote. That's all you need to learn to write a Ray program. After adding the decorator, the function becomes a distributed task, and the class becomes a stateful actor. You can call .remote to execute, Ray.get to collect the result. Now, I want to spend some time to talk about Ray's architecture, and we are going to use it later. This is what a Ray cluster looks like. In a very, very high level, it looks very, very similar to Kubernetes. They both are resource orchestrator, but at different layer. Ray is process level orchestration. Kubernetes is container level orchestration. And Ray schedules Python functions and classes. Kubernetes schedules containers. On the left, you have the control plane, the head node. It stores cluster metadata and handles scheduling and auto-scaling decisions. On the right, you have the data plane, the worker nodes. This is where your actual workloads run. And now, let's talk about how to run Ray on Kubernetes. Here is our today's main character, KubeRay. So Ray focuses on application layer, and it handles process orchestration. Kubernetes focuses on container layer, and it handles container orchestration. KubeRay bridges these two layers. It's a Kubernetes operator that manages the life cycle of Ray applications on Kubernetes. Kubernetes prepares resource to run application, and Ray decides how the application is going to use the resource. KubeRay provides 3 API, or you can understand as 3 CRD. Ray cluster for managing Ray cluster we just seen before, and you can run any AI workloads in a Ray cluster. Ray job for workloads like distributed training or batch inference. It creates a cluster, runs a job, and cleans up. A Ray service, which is what we will focus on today. It manages both the cluster and Ray serve application with 0 downtime upgrades and high availability. Next, I'm going to talk about key features in Ray service. The first feature is in-place update for serving applications. Imagine you're running ChatGPT 5.3 on a Ray cluster, and you want to upgrade to ChatGPT 5.4. With in-place update, you don't need to create a new cluster. You simply update the serve config in your Ray service manifest. And that's it. KubeRay detects the change. It sends an HTTP request to the Ray control plane API server, and Ray serve handles the rolling update internally. All within the same cluster. So no new cluster, no downtime, no wasted resource. We just need to update the config and apply it. The second feature is 0 downtime upgrade. So when you want to upgrade the entire Ray cluster, during the 0 downtime upgrade process, KubeRay will create a new Ray cluster temporarily and wait for it to become ready. Once the new Ray cluster is ready, the Kubernetes service here will switch the traffic to the new Ray cluster. And finally, KubeRay will delete the old Ray cluster. The third feature I want to talk about is high availability. So serving AI models in production means you have to dealing with failures. For example, a replica process can crash, a node can go down, or even the whole Ray cluster crash. Restart the Ray cluster can take a lot of time. KubeRay plus RayServe handles recovery automatically at every layer. RayServe helps data planes replica to restart. KubeRay helps control plane and data plane nodes restart in the Kubernetes cluster. Let's talk about auto-scaling. So AI inference traffic is bursty, and a service can go from near zero to thousands of requests in seconds. In Kubernetes with Reserve, autoscaling happens in 3 layers. Layer 1 is the Reserve autoscaler. It scales serve replicas based on request pressure, queue size, and ongoing requests, rather than just resource utilization. If the RAID cluster already has a spare capacity, new replicas can start quickly as RAID actors on existing RAID nodes. Layer 2 is the RAID autoscaler. So when the current cluster no longer has enough logical resource to place those replicas, RAID adds worker pods. Because RAID understands the workload's resource requirements, it can scale the appropriate worker group. For example, GPU workers for the large language model deployment and CPU workers for preprocessing. Layer 3 is the Kubernetes cluster autoscaler. If the new RAID worker pods can't be scheduled because the Kubernetes cluster is out of capacity, Kubernetes provisions new nodes. So these 3 layers work together. Serve layer scales the application, RAID scales the worker pod, and Kubernetes scales the cluster by adding Kubernetes node. I want to mention 2 points specially. Unlike the default Kubernetes HPA setup, while often scales on CPU or memory utilization, Reserve is natively request-aware and scales based on queue depth and ongoing requests. And if the building policy is not enough, Reserve also lets you define a custom auto-scaling policy. And Kubernetes, right now I want to talk about its ecosystem. Kubernetes integrates with the Kubernetes ecosystem you already use. For scheduling, we support queue, including multi-queue for multi-cluster job dispatching, as well as Volcano, Apache Unicorn, NVIDIA's Kai scheduler, and the Kubernetes scheduler plugin. Whether you need Gantt scheduling, priority queues, or GPU sharing, Kubernetes works with your batch scheduler of choice. For observability, Kubernetes exports RAID metrics to Prometheus and ships with pre-built Grafana dashboards. So you can monitor cluster health, auto-scaling, and request latency through the same monitoring stack you already have. And if you need to provide a running workload, we support PySpy integration for CPU flame graphs directly from the RAID dashboard. Finally, I want to introduce a new feature in RAID and Kubernetes, the history server. Many teams run RAID cluster as ephemeral units. They spin out a cluster, run the job, and tear it down. This saves resource costs. But when the job fails and the cluster is gone, you lose the RAID dashboard, your primary debugging tool. The history server fixes this. While a cluster is alive, it automatically collects cluster metadata and logs into persistent storage like S3 or GCS. After the cluster is deleted, the history server restores the dashboard from that data. So you can debug a terminated RAID cluster as if it was still running with no RAID cluster resource cost. And the Kubernetes history server is mainly designed and developed by Anyscale, Google GKE, and Alibaba ACK. Finally, please join the community. Please join our RAID Slack, and here we have a lot of RAID masters from Anyscale can answer your question. Also, please join Karmada Slack to ask more questions. They are in CNCF Karmada channel. Thank you, everyone.